In order to talk about the concept of standard deviation, we first need to review a few other vocabulary terms. The first are mean and median, which you know from middle school math and Algebra 1 are measures of central tendency. Mean is sometimes represented by the Greek letter mu. It's also sometimes represented by the variable x with a bar over the top of it, and it's typically read as x bar when we see it in that case. So these are two different common symbols that you'll see for the mean. You know from past study that the mean is calculated by adding together the values in a list and then dividing by the number of values in that list. The median is another measure of central tendency, which we calculate simply by putting all the numbers in order, crossing them off from the ends until there's either one number left in the middle, or we take the mean of the two values left in the middle. Now, when we are looking at distributions of data, we will often talk about the shape of the distribution. So typically we are looking at bell-shaped curves, which is what you see down here in the normal curve. But you can also have data that's bimodal. Basically, it has peaks in two different areas of the graph. It could be irregular, so it doesn't really fit a particular pattern, or the data could be rather uniform, where all of the data is at approximately the same height, and so it's hard to apply something like a normal distribution analysis to data that isn't shaped in a basic normal distribution. So then we get to the normal distribution, which is what the standard deviation is being applied to. So a normal distribution is a distribution of data set that appears symmetrical and creates a bell-shaped curve with equal values for the mean and the median. So when we have this, it's not skewed one way or the other. Most of the values are peaking in the middle, and then it's kind of dropping off on either side like you see in the shape of this curve overall. And the normal distribution is very interesting because it's predictably dividing out the data into certain percentages. So you'll notice across the bottom, we see that mu that we were talking about before. And then we have this other Greek letter here, which is a lowercase sigma. And this is what's used for the standard deviation itself. So what we see here is these vertical bars on the graph are one standard deviation above and one standard deviation below the mean. So all data in these two bars, I'm not sure why both of those disappeared, but all of this data in here, which is 60% of the total data under the normal curve, they're all within one standard deviation of the mean, either one standard deviation above the mean or one standard deviation below the mean. Now you'll notice these next vertical bars have the same width. And once you've added on two standard deviations above and below the mean, now you're including 95% of all the data under the normal curve. And then if we add on a third standard deviation above or below the mean, we've now captured 99.7% of all of the data under the normal curve. So when you have data that's distributed this way, you have predictable percentages of the data in these different regions of the graph. So down below we have the standard deviation, which is a measure of spread for a set of numerical data. So a measure of spread would be something like the range or the interquartile range. Instead of focusing on what's going on at the middle of the data, it's asking how spread out is the data. And it's calculated by taking the square root of the variance, which increases in value as the data set become more and more spread out. So this fairly fancy definition, there's a few things I want you to take away. The biggest is a large standard deviation means that the data is spread out. While a small standard deviation means that the data is consistent or grouped towards the center. Now, we won't really talk about variance because we're not going to be calculating standard deviations by hand, but just because that word comes up in the definition, variance is a measure of variability in a data set. calculated by first finding the numerical difference between each value in the data set and the mean of that data set, then squaring those differences, and then finding the average of all of those squared differences. Both this diagram and all of the definitions that are given here are taken from the website that's cited at the bottom of the note sheet. So you could always check that out if you want to get a little bit more information about each of these terms. What we want to do now is take a look at the types of questions that you want to be able to answer, both because that's what you'll see in your homework and also because these are the types of or the level of questions that you might see on an SAT. The first question asks, the table to the right displays the number of sales a salesperson made each month during the past 15 months. So if you look off at the table, you can see the months are numbered from 1 to 15. And then in the second column, we have the number of sales that were made during each month. We're told that the mean for this data set is 4.4, and the standard deviation is approximately 1.82. We are asked within how many standard deviations of the mean do all of the data fall. So if we were to take a look at this data, we might want to start by kind of grouping it into like a line plot, which falls along a number line. So if I quickly sketch in a number line and I look at the data that we have, as I'm scanning through, I see that the lowest number seems to be a 1 and the highest number seems to be an 8. So if I make a number line, evenly spacing my data from 1 to 8, I can then go in and create a quick line plot to get a visual image of what this data looks like. So I believe there was only 1, but I see there's a 2. That looks like maybe it's the only 2. And then we have a 3 and another 3 and another 3. So there are 3 3s. And you'll notice I'm trying to space these evenly as I go up, just like we spaced them evenly as we went from side to side. After 3, we've got 4, so there's 1, 2, 3 4s. 4 5s, we have 1, 2, 3 5s. And then I see a 6 and another 6. There's a 7, and there's an 8. So it looks like that's how our data falls out. Now, this doesn't have a high peak in the middle, but it does roughly follow that idea of a bell-shaped curve. It peaks towards the middle, it trails off to each side. So we can consider what this looks like in terms of a normal curve. So what we also might want to do then is to go ahead and take a look at where those standard deviations would fall. So they tell us that the mean falls here at 4.4, and that the width of a standard deviation is 1.82. So if you take 4.4 and you add 1.82, you'll get 6.2. So the first standard deviation goes to about here at 6.22. If you go in the other direction, subtracting the 1.82 from the 4.4, one standard deviation the other direction lands right about here at 2.58. So quite a lot of the data, it should be 68% of the data, will fall between those two bars and be within one standard deviation of the mean. Now, if I want to know the second standard deviation of the mean, well, first I can take the 6.22 and add another 1.82. So I'm adding the standard deviation onto that next value, and that will bring me to 8.04. So all of the data on the high end are within 2 standard deviations of the mean, and we need to look at what happens on the low end. So we would take the 2.58 and subtract that 1.82, which brings us to 0.76. So just like on the high end, we see that on the low end, we're within 2 standard deviations of the mean. So to answer the question, within how many standard deviations of the mean do all of the data fall? Well, it's within 2 standard deviations. Another type of question we should be asking is to interpret some line plots that are given to us. So first, we would want to make sure we understood what was going on in the graphs. I see that these plots are both scores of 2 classes on a quiz. So class A has the scores as shown up above. It looks like they were scored out of 5 points on this quiz. And class B has the scores shown below. Now, we would call class B a uniform display of data because like 4 kids got a 0, 4 kids got a 1, 4 kids got a 2. There's a consistent height to the bars all the way across this line plot. Whereas the data for class A, it's not really a bell-shaped curve. It's a little bit skewed. You can see that on the left, the data trails off a little bit in that direction, so it's skewed to that side. But it's certainly not uniform like the data in class B is. All right, now that we've thought a little bit about what we're seeing in this data, let's take a look at question number 2. It says the dot plots to the left summarize the scores that 2 classes, each with 24 students at Central High School, achieved on a current events quiz. We're asked which of the following correctly compares the standard deviation of the scores in each of the classes. So before we try to answer this question, we want to remember what we talked about on the first page when we were first talking about standard deviation. Remember, when the data is clustered close to the mean, we're going to have a small standard deviation. And when a lot of the data is far from the mean, we're going to have a large standard deviation. So if you're thinking in terms of a bell curve, you want to see a lot of data at the peak of the bell. If I try to imagine a bell curve on class B, it doesn't really make any sense. We have tons of data above the bell curve instead of under the curve. So we would expect this to have a large standard deviation. Whereas we would expect this to have a smaller standard deviation. We would expect the mean to fall in here somewhere, around 3 point something, and most of the data is clustered closely to that mean. So now let's read the multiple choice options. It says the standard deviation of the scores in class A is smaller. Well, that's what we kind of decided when we looked at the data. So my first instinct is that that is the answer. But on the SATs, I always want to be careful to read all of the multiple choice options and make sure there's not something else that could also be a correct answer. B says the standard deviation of the scores in class B is smaller, and that's incorrect. We said that standard deviation would be bigger. C says the standard deviation of scores in these 2 classes is the same, and that would not be true when you have one set of data that is very uniform and one set that looks much more like a bell curve. They will not have the same standard deviation. And then the other option is that this relationship cannot be determined from the information given, and sometimes that's a viable answer, but we can conclude based on what we see that the standard deviation must be smaller for A, so we can go ahead and circle that answer, which was our initial instinct as to what would be correct. Now, in number 3, we're asked to describe the shape of the distribution for class A and to determine which measures of center and spread would best represent the data. So we need to go back and say, okay, so this looked like a distribution that's pretty close to a normal distribution. So it's similar to a normal distribution, even though it's a little bit skewed. And we're asked which measures of center and spread best represent the data. Well, first let's talk about center. When we're talking about measures of center, our options are mean, median, and mode. And we actually haven't talked about mode yet today, but remember, mode is just the value that occurs most often. And that's not typically your best measure of central tendency, because if it is your best measure of central tendency, it happens to also agree with either the mean or the median or both. So it's never really what we look to as the best measure of central tendency. It just tells us what's most common. So typically, we want to choose the mean unless there's an outlier, a number that's significantly bigger or significantly smaller than other data values within the data set. And if there is an outlier, then we do choose the median, because the median is not as influenced by the presence of an outlier. So if there is an outlier. Now, in this data set, there doesn't really seem to be an outlier. There's no value that's way smaller than everything else or way bigger than everything else. So I would say the mean is the best measure of central tendency. Now, when it comes to measures of spread, we have things like the range or the interquartile range or the standard deviation. Now, when we're trying to compare these two classes, the range is not very helpful because the range for both of these classes is the same. 5 minus 0 is 5, and 5 minus 0 is 5. So I can't really compare these data sets and distinguish them in any meaningful way by looking at their range. So the range is not a great measure of central tendency in this context. Rather, the standard deviation would be a good option because it is going to highlight how much more clustered together the data is in class A versus class B. You would have a very big standard deviation because a lot of the values deviate from the mean. A lot of the values are far from the mean. So I would say that the mean for a measure of central tendency and the standard deviation as a measure of spread is probably the best way to distinguish class A from class B. Now we're going to take a look at a box and whisker plot, which is another representation of data that you're likely to see on the SATs and you could run into in everyday life, either in advertising or medical literature. So we'll take a look at this box and whisker plot to the right. It says the distribution of scores for a test given to a large group of students is represented by the, it says above, but it should say to the right box and whisker plot. To the nearest whole number, we're asked what was the standard deviation of the scores. Now, in order to calculate a standard deviation, we need to see all the data. We really can't calculate a standard deviation from a box and whisker plot. Now, it's possible that they could give us answers that we can absolutely rule out as being unreasonable, but we really are being asked to know that I can't calculate standard deviation from just the 5-number summary. So when I look at something like this, I'm like, well, the minimum value is 23, 8, 12, 18. Like, I don't know how big the standard deviation will be by just looking at the data. I can see that, like, there's more numbers on a bigger range on the high end above the median than there is on the low end. I can see that there are whiskers here to the box and whisker plot, but it doesn't really look like there's any extreme outliers. Like, I could calculate the IQR to figure that out. But again, that's just telling me, is it going to be a biggish standard deviation or a smallish? It's not really telling me what the answer is. So in this case, I would have to say A. I can't calculate the standard deviation because I can't see the individual data values. I just see this summary of what the data looks like. Now we go on to question number 5. It says the list to the right include the test scores in increasing order for 2 of Mr. Perlman's classes, each of which has 6 students. So these are some very tiny classes. Which of the following correctly compares the standard deviation of the scores for each class and explain? So kind of like we did before, we want to kind of wrap our heads around what's going on in this data before we try to look at the multiple choice questions. Now, as I start, I'm looking at class A. I see we've got a low end of 68, a high end of 99. There's quite a few grades in the 90s and then like one each in the 60s, the 70s, and the 80s. So there's like a cluster of grades at the high end, and then they kind of trail off down to the left. Whereas when I look at class B, the lowest is 85 and the highest is 90. So the minimum here is significantly bigger than the minimum in class A, but the maximum in class B is substantially smaller than the maximum in class A. There's a lot more consistency here. So here I would expect a small standard deviation, whereas where the data is more spread out, I would expect a larger standard deviation. So looking through the options, it says the standard deviation in the scores of class A is smaller, the standard deviation in B is smaller, the two are equal, or the relationship cannot be determined. Well, given that the data is grouped so closely together, in class B, I would expect a smaller standard deviation. So I'm going to choose option B. Next, we are asked to use a graphing calculator to find the mean, standard deviation, and 5-number summary for class A. Since I've hit the 20-minute mark on this video, it's going to be a lot to upload. I'm going to stop the video and start a second part 2 video to pick up where I left off with this question.